We're going to start section 6.5, which is on matrix products and inverses. This video is going to focus entirely on matrix products. So our next video will focus on inverses. I do want to make a point to say that we will always be multiplying a row by a column. So notice in the example here, we're multiplying a 1 by 3 matrix times a 3 by 1 matrix. Remember that the size of the matrix always describes the number of entries in the row first and then the number of entries in the column. So this first matrix would be a 1 by 3 matrix, and then this matrix would be a 3 by 1 matrix. And we were also calling these, the first matrix a row matrix, and the second matrix will be a column matrix. So throughout this whole video, we're just going to be multiplying a specific row by a specific column. It is important that the number of entries here match. So notice that we have 3 entries in this first row and then 3 entries in this first column. And therefore, this matrix product is going to be well defined. It should result in a 1 by 1 matrix. And the way that we compute that product is we just take the pairwise products of the first terms. So we'll get a 1 times 6, and then plus a 2 times -5, plus a 3 times 0. So we just take the product of the first terms plus the product of the second terms plus the product of the third terms. Okay, and that ends up giving us the final result, which is -4. It's okay to write this as a -4 in brackets if you want to emphasize that it's a 1 by 1 matrix. But remember, we identify 1 by 1 matrices with scalars. So it's okay to just write -4 here. So we're going to apply the same principle here in 1a. We're going to compute this product. This is, again, a 1 by 3 times a 3 by 1 matrix, which should result in a 1 by 1 matrix. Remember that those inner numbers have to match. So here, because the number of columns of the first matrix matches the row number of the second matrix, that product is well defined. The same thing is true here. And the way that we compute the product is we'll take the first entries, multiply them together, plus the second entries when we multiply them together, plus the third entries when we multiply them together. Now, I do expect that as you start to get comfortable with this, you won't need this scratch work. You'll be able to just compute the product of a specific row and specific column mentally. So this would end up being a -1 minus a 3 plus 0, which we can compute to be -4. And I expect that we'll start to be able to just compute these mentally by just jumping straight to this row, where we have the product of the first terms is a -1, the product of the second terms is a -3, and the product of the last terms is a 0, and then you can total these up mentally. So if you want some practice with that, what you can do is you can compute 1b here. I'd advise you to maybe pause the video and compute this on your own just to make sure that you're understanding this correctly. So I'll let you do that. Now this one is a 1 by 4 matrix times a 4 by 1 matrix. So again, we should end up getting a 1 by 1 matrix, or in other words, a scalar. The product of the first 2 entries is a 10, and then the product of the next entries is a -10. The product of the third entries is a 4, and the product of the last entries is a 0. Now, ordinarily, I would just compute that sum mentally, but it's okay to write some scratch work if you'd like. This would be a 10 minus a 10 plus a 4 plus 0, which is a +4. So that product will be a +4. Okay, and then lastly, we'll look at this one. Here we again have a row matrix times a column matrix. But unfortunately, the sizes don't match here. So anytime you see something like this, we're trying to multiply a 1 by 4 matrix times a 2 by 1 matrix. And because these inner numbers don't match, this product will not be defined. So it's okay to just say something like product undefined. Okay, or even just undefined is fine. Sorry about that. There we go. Still learning how to scroll on this thing. Okay, so next let's talk about more general matrix products. For this first example, we're just going to be talking about whether the product is defined. So we're not going to actually compute the product, we just want to know whether the specific matrix product that's written down here is well defined. And for this, the guidelines exist up here. So notice that if A is an m by n matrix and B is an n by k matrix, then this product would be well defined and the result would be an m by k matrix. So just to give you an example that involves real numbers, maybe I'll write one down up here. So let's say that you're trying to multiply a 7 by 5 matrix times a 5 by 3 matrix. That product would be well defined because the column number from the first matrix matches the row number from the second matrix, and the resulting matrix would be a 7 by 3 matrix. Okay, so that's all that this first rule is saying. And let's apply that rule in this example 2. So in example 2, we're told that A is a 2 by 3 matrix. B is clearly a 3 by 2 matrix. Remember, you write down the number of rows that the matrix has and then the number of columns. So B would be a 3 by 2 matrix. And C is a 2 by 2 matrix. So we just need to know which of the following products are defined, and if the product is defined, what would the resulting product be? What would the order of that resulting product be? So if we want A times B, that would be a 2 by 3 matrix times the matrix B, which is a 3 by 2. And this product would be well defined. You can pause the video if you need some time to think about it, but you should first decide what the size of the resulting product would be. And this one will end up being a 2 by 2 matrix. So that would be the size of AB. Now remember that what we're looking for here is that these middle terms match. If you take the size of the left matrix and then the size of the right matrix, we need those middle numbers to match. So the column number for A matches the row number for B. And when that happens, you can think of those as canceling out, and what you're left with is just these outer sizes. So you're going to get a 2 by 2 matrix. Okay. We can do something similar for B times A. So notice that here B is the left matrix, so we're trying to multiply a 3 by 2 matrix times the matrix A, which is a 2 by 3 matrix. Now again, these column and row numbers match. This time they're inverted. So we have a 3 by 2 times a 2 by 3. The middle terms match, so we end up getting a 3 by 3 matrix. So both of those products are well defined. There is something sort of strange here in that notice that the matrix AB was a 2 by 2 matrix and the matrix BA was a 3 by 3 matrix, and in particular those can't be the same matrix. So AB is not going to be the same matrix as BA. This is something weird that comes up whenever you have matrix multiplication. Matrix multiplication is what's called non-commutative, and that's what this corollary down at the bottom says. So it says that because those two matrices have different sizes, they can't be the same matrix. AB equals BA is true for scalars, but AB and BA are not necessarily the same whenever you turn to matricial products. Okay, so let's go ahead and finish the rest of example 2. I just wanted to point out that this is a little bit strange because we're used to having commutativity of multiplication, and that no longer holds in the context of matrix multiplication. So the order does matter here. So next, let's look at C. Here we're trying to multiply the matrix A by the matrix C. So this would be a 2 by 3 matrix times a 2 by 2 matrix, because C is a 2 by 2 matrix. And in this case, because the column number for A does not match the row number for C, this would be an undefined product. So we won't try to define a matrix product in this situation. We would just call this undefined. So notice that if you multiply by A on the left and C on the right, that product is undefined. Now let's look at what happens when we switch them. So we'll take C times A. C was a 2 by 2 matrix. A was a 2 by 3 matrix. And notice that just by switching the order here, now we do have a well-defined product. The inner terms match here, so we have a 2 and a 2. And therefore this product will be defined. and the size of the product will be those outer numbers, so it will be a 2 by 3 matrix. Okay, so the resulting product CA would be a 2 by 3 matrix. Okay, so now we're going to actually talk about how to compute products rather than just determining their sizes. But it is important to first note the size of the product before you start to compute it. So in this example, in 3a, we have a 2 by 2 matrix times another 2 by 2 matrix. And using the logic above, what we have is that the resultant should be another 2 by 2 matrix. So the resulting matrix will be a 2 by 2 matrix like this. And our goal is to compute those 4 numbers, the 4 entries in the resulting product. And thankfully, we got to talk about this a little bit before the break, but remember that the way that you decide how to compute the specific entries is you decide which row and which column to multiply from the original matrix based on the position of the entry that you want to compute. So for example, let's first focus on this first entry. So this is the entry that lives in the first row and the first column. Now, the location of that entry will tell you which row from the left matrix and which column from the right matrix to multiply. So in this case, if we want to compute the 1, 1 entry, we would multiply the first column, which I circled, the first row, which I circled, times the first column, which I also circled. So we're going to compute that product. Now, I am going to start computing these mentally. If you need to take some time to pause the video and do some scratch work, then you're welcome to. But I'm going to compute this product here. This would be a 2 times an 8 plus a 3 times a 9. So that would be a 16 plus a 27, which is 43. So this first entry will be a 43. Okay. And now we'll do the same thing. So actually, I'm going to erase these so that I don't have all these circles. So we just computed that this first entry is a 43. And now we'll move on to the next entry. I prefer to just compute these row by row. So I'll stick with the first row and we'll be working on this second entry in the first row. So because I'm looking at the 1, 2 entry of this matrix, I'll multiply the first row here. So I'll multiply this row by the second column now. So it'll be this row times this column. And that would be a 2 times a 7, which is 14, minus a 3. So that's a 14 minus 3, which gives me an 11. So again, I'm going to backspace a little bit so that we don't have all that notation. But we just computed that the 1, 2 entry of the product is an 11. Okay, and then we'll do the same thing for these other entries. So this time I want to compute the entry that lives in the second row and first column. So I should multiply the second row by the first column. That would be this row times this column. So that would give me a 1 times 8 plus 11 times 9. So that's an 8 plus a 99, which is a 107. So this entry will be a 107. And then similarly, if we want to compute the 2, 2 entry here, then we would just multiply the second row by the second column. So we'll take this times this, and that would be a 1 times 7 minus an 11. So 7 minus 11 will give me a negative 4. And this is the resulting product. Okay, so basically, whenever it comes to computing matrix products, you'll always be multiplying a specific row by a specific column. And the way that you decide which row and which column to multiply is just based on the location of the entry that you want to compute. So for example, if we were computing this entry down here, the bottom left entry, because it lives in the second row in the first column, that tells me that I should multiply the second row in the first column. Okay, and we'll compute some more matrix products in the next video, but I think I'll call it for this one.